A very good morning, sir. I am J. Mohammed Hani from CSCB section, and the topic given for my presentation is direct and indirect bandgap semiconductors. Moving on to the outline of the presentation. So here we have introduction of semiconductors, representation of the direct and indirect bandgap semiconductors, and we'll learn in detail about what are direct bandgap semiconductors, what is indirect bandgap semiconductors, and finally we will be able to draft the differences between direct and indirect bandgap semiconductors. So before going into the topic of direct and indirect bandgap semiconductors, first we will learn what are semiconductors. So basically, semiconductors are materials which have a conductivity between conductors and non-conductors, that is insulators. The energy band gap between the valence band and electron band would be like average energy gap. So the materials which fall in under this graph are called as semiconductors. These can be pure elements such as silicon and germanium, or compounds such as gallium arsenide and cadmium selenide. These are the examples of semiconductors. Semiconductors are an essential component of electronic devices, enabling advances in communications, common healthcare, military systems, transportation, clean, and countless other applications. So these are the applications of semiconductors. Now we'll move on to the introduction to direct and indirect band gap semiconductors. So here we have, these are the materials with a specific energy gap between valence band and conduction band. Since these are semiconductors, as we have already discussed about the specific energy gap which fall under semiconductors, these are band gap semiconductors. This energy gap determines the semiconductor's electrical properties. Two main types of band gap semiconductors are direct and indirect band gap materials. That is, here they are telling that based upon the different band gap, the semiconductors are divided into two types. One is direct band gap semiconductors, and the other is indirect band gap semiconductors. Talking about the direct band gap semiconductors, in direct band gap semiconductors, the minimum energy of the conduction band aligns with the maximum energy of the valence band at the same momentum. Which we'll learn by seeing looking at the further diagram, and this allows for efficient light transmission and absorption process. Example of direct bandgap semiconductors include gallium arsenide and indium phosphide. Coming to the indirect bandgap semiconductors, in indirect bandgap semiconductors, the minimum energy of the conduction band does not align with the maximum energy of the valence band at the same momentum. In the sense, the maximum of the conduction band and the minimum of the valence band would not be aligned in the same direction. There would be some difference in the momentum. So these come under indirect bandgap semiconductors, and they are lower in efficiency for light transmission and absorption when compared to direct bandgap materials. And a common example for indirect bandgap semiconductor is silicon. So now we'll be looking about the representation of direct and indirect bandgap semiconductors. So here we could see that in the direct bandgap semiconductors, the maximum of the valence band and the minimum of the conduction band are separated by some particular energy gap, and these are in same phase, that is same direction, without any change in momentum. For example, when an electron and the hole want to recombine, the electron hole recombination occurs without any change in momentum. And here, when we look into indirect band gap semiconductors, the maximum of valence band and the minimum of conduction band are separated by some energy gap, but when electron hole recombination takes place and there occurs a difference in momentum. That is a main difference between direct bandgap semiconductors and indirect bandgap semiconductors. So here we get a doubt of why are we representing the conduction band and valence band in parabola shape. So for this we have basically the energy is directly proportional to the momentum. Since momentum is equals to h cross k, where k is wave constant, so E is also directly proportional to the k square. Because of this quadratic relationship between energy and the wave constant, we are representing the conduction band and valence band in two parabolas. Coming to the description of the band diagram that we have seen now, in the direct bandgap semiconductor, the energy band diagram shows a direct transition from the valence band to the conduction band. So in direct bandgap semiconductors, the transition of the hole and electron is direct transition without any change in momentum. And this direct transition allows for the efficient generation of photons during electron hole recombination, as we have discussed about this point already. And these materials are commonly used in optoelectronic devices like LEDs, emitting diodes, and lasers. Because of this wide applications, we are easily using the direct bandgap semiconductors in the production of optoelectronic devices. Talking about the energy band diagram of indirect bandgap semiconductors, in an indirect bandgap semiconductor, the energy band diagram shows an indirect transition between the valence band and the conduction band. Since we have already seen in the diagram that there is an indirect transition but not direct transition. This is because the difference in momentum when electron and the hole recombination takes place. And this indirect transition leads to lower efficiency in light emission and absorption processes. And the materials that are often used in electronic devices like transistors and solar cells. That is, indirect bandgap semiconductors are useful in the production of the transistors and solar cells. Now we'll look into the properties of direct bandgap semiconductors. These have a higher absorption coefficient for light compared to indirect bandgap materials, since this point is already repeated, and this exhibit faster electronic hole recombination rates, making them ideal for high-speed optoelectronic applications. So the main advantage of direct bandgap semiconductors, there is no change in momentum when electron hole recombination takes place, and also electron hole recombination rate is faster when compared to the indirect bandgap semiconductor. Direct bandgap materials are preferred for devices requiring higher light emission, such as lasers and also. Now moving on to the properties of indirect bandgap semiconductors. These have longer electron lifetimes due to the nature of their indirect transitions. So here, changing momentum occurs, which leading to the indirect transition, and thereby it leads to the longer electron lifetimes. And they have lower efficiency in light emission and absorption compared to direct bandgap materials. This is something that is different from direct bandgap semiconductors. And also, indirect bandgap semiconductors are commonly used in electronic devices that do not require high efficiency light emission. Now we'll move on to the applications of direct bandgap semiconductors. So basically, direct bandgap semiconductors are widely used in optoelectronic devices such as light emitting diodes and laser diodes. They are essential in applications requiring higher light emission and absorption, such as telecommunications and sensing. This point is to be highlighted that direct bandgap semiconductors are used in telecommunication devices and sensing devices. And direct bandgap semiconductors are also used in photovoltaic cells and photodetectors for energy conversion and detection purposes. Now let us move on to the applications of indirect bandgap semiconductors. These are commonly used in electronic devices like transistors, computer chips, and integrated circuits, that is ICs, and they are preferred for applications where efficient light emission is not a primary requirement. Since they have lower efficient light emission, these depend on the applications that are required for the production of different materials. These are commonly used in solar cells for energy harvesting and power generation. So, in conclusion, understanding the differences between direct and indirect bandgap semiconductors is crucial for designing and optimizing semiconductor devices. So, for the production of semiconductor devices, based on the different applications, we have to understand the basic differences between the direct and indirect bandgap semiconductors. So, which leads the effective production of the devices. And direct bandgap materials offer higher efficiency in light emission and absorption process, making them suitable for optoelectronic applications. And indirect bandgap semiconductors are preferred for electronic devices that prioritize electrical conductivity and different light emission efficiency. So based on the different types of properties and applications of bandgap materials only, we are going to use these bandgap semiconductors in production of either optoelectronic applications or different electronic devices based on their priorities. I hope I have clearly demonstrated the differences, applications, and everything about direct and indirect bandgap semiconductors. And thank you for your patience listening.